We're going to have dinner with Jonathan at Changsha, leaving here around 6. And if you would like to add yourselves to the company, come and see me after the talk.
Remember, students are free.
Yeah, free for graduate students, discount for postdocs, faculty pay full price, at least full price. Okay, Jonathan McDowell came originally to us from Cambridge, where he did his PhD in a kind of golden era of cosmology there. And he didn't want me to say this, but he claims that at one point he changed Stephen Hawking's mind about some important issue. So you can ask him about that later, or not. He then went to Jodrell Bank, where he worked with, where oddly he worked with Suzy Collins in France, who was a famous AGN expert. But then I managed to lure him to CFA to work on spectral energy distributions of quasars, which was a very successful thing, and I got lots of citations out of it. He did as well, but anyway. But he did most of the work. And he's pretty much stayed here ever since, with a little deviation to Huntsville for a year or two, because he wanted to see shuttle main engines being tested. Here he came back to work on Einstein, the old, very important imaging X-ray observatory, and he started working on something which sounds incredibly boring, but it's actually more important than almost anything any of us have done in astronomy, and that is work on data standards, so that you could have interchangeability and display radio on top of optical on top of X-ray. And all that began with the work he did when he was on Einstein. But today, he's not here because of his astrophysics so much as because of his peculiar hobby, which goes back to before you were an undergraduate, right?
Oh yeah, since I was about 13.
Okay, where he got this strange obsession with tracking all human space objects, literally everyone. At one point, you could just ask him, what's the name of this glove that is orbiting? He would tell you, although it has deorbited since, I believe. I think it's got a little beyond that now, right?
It's hard to keep up now.
Yes. But the result of this is it went from hobby to obsession to there's another level where he just burst out to become an expert. And in fact, his database, which you can see at Planet 4589, his named asteroid, which has a lower number than mine, is actually better than the ESA database or the NASA database, or so far as we know, the Department of Defense database. It's acknowledged as the best public database, at least in the world. And he did all this on evenings and weekends, and lots of vacations in dusty archives all over the planet. It's a very strange thing to specialize in from my point of view, but it's obviously done great things for Jonathan. However, suddenly, it had nothing to do with astronomy, but suddenly, because of SpaceX Starlink constellation, suddenly astronomers are very interested in his database and the results that come out of it. So his two streams of work and hobby and work have combined, and he's going to talk to us today about a sky full of satellites. Thank you.
Thank you very much, Martin. We are on the way to having a sky full of satellites, and that has implications for astronomy, particularly optical astronomy from the ground. And when I was an undergrad summer intern at the Royal Greenwich Observatory in the early 1980s, my boss was FGS, Francis Graham Smith, who already at that time, in a talk in 1980, published in 82, said, "The cumulative effect of an increasing number of long-lived satellites represents a very serious hazard to astronomy." And that was when there were only 350 working satellites in orbit. There are 20 times that many today. So he was pretty prescient. Now we have a problem. And I'm going to go through this. This is just sort of my plan. I'll introduce the issue. I'm going to do a little digression into the demographics of the satellite population more generally to give you some context. I'm going to do some simulations of how bad it's likely to get for an observer on the ground. I'm going to talk about how we monitor what the space companies are actually doing. I'm going to give you some good news about what SpaceX is doing to mitigate the brightness of these satellites. And then I'm going to talk briefly at the end about the astronomy policy response. And I want to thank this long list of collaborators, notably Connie Walker, who's really leading the effort here in the US, Richard Green doing a lot of work on policy, Meredith Rawls on the observing side, and a cast of some amazing characters around the world. So I'm going to start off by talking about the problem. More and more frequently, you get these streaks on ground-based astronomy images, and there are some are short and some are long and some are fat and some are blobby like this. You can imagine this tumbling object, flare, 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 could easily be detected as fake sources in a source detection program. So it's not a trivial thing to get rid of them, even when they're sort of somewhat rare. You can do some medium filtering. When it gets to the level of more than one per wide field image, then it starts to be a real problem. So I'm going to just mention, I'm only going to be talking about the effects on optical astronomy. There is a big threat to radio astronomy, which I'm just going to ignore. Those of you who remember Ashley Zouderer from her time here is now at NSF, working on these issues, as well as Harvey List. So you should get one of them here to tell you about that. So in May 2019, SpaceX launched the first 60 Starlink satellites on a single rocket. And the next day, Marco Lambrook in the Netherlands took this image of 60 magnitude 2 objects crossing the sky. And we kind of went, oh, that's brighter than we expected. What happens when there are 100,000 of these, like the companies are talking about? That could be bad. And so we started actually paying attention, which we hadn't been before. And so I organized a bunch of satellite hobbyists to do some early measurements of brightness once the satellites oriented themselves and raised their orbits to 550 kilometers instead of the deployment altitude near 300. They were significantly fainter. And this histogram shows how bright they were. This is only the satellites that reached that higher 550 kilometer orbit, and they're mostly magnitude 5 or 6, although there is a bright tail to 3 or 4, even at that altitude. And so they are largely naked eye objects in the summer of 2019 here. And this is from a paper I published in 2020. And when they come off the rocket, they're this much brighter train of satellites. And here's some pictures from around the world of these Starlink satellite trains from different launches, showing them in the sky. So they've done some mitigations. The satellites are a bit fainter, but they're still, some of the time, naked eye in dark skies. But more importantly, that very first observation shows that it is technically possible. If you are a supervillain whose goal in life is to destroy ground-based astronomy, and you're a billionaire, you do now have the technology to deploy a very bright constellation of satellites in low orbit that would outnumber the visible stars, and change the night sky for everyone. And so you might think that even if you're, in a spacefaring not in a spacefaring nation, but a nation that still, maybe cares about the night sky for cultural reasons, you might want to have a say in this, rather than it just being one country's regulatory authority that approves this happening. And so there is nothing right now. There's no global regulation that would stop some other country licensing an extremely bright constellation of many thousands of satellites, as we shall see. So I'm using the word constellation. I thought I should emphasize that I'm not talking about Vulpecula and Ursa Major. These are satellite constellations, a whole bunch of satellites owned by the same organization, carrying out the same mission in similar orbits. And so what do you do to make a satellite constellation? You put a bunch of satellites in an orbit. Let's look at this 3A, 3B, 3C orbit here. Spread them out along the orbit. And then you do the same thing in another orbit with a longitude of ascending node that's maybe 20 degrees to the east. And again, and again, and again, until you have a shell of satellites in orbits surrounding the Earth at a particular height and a particular orbital inclination to the equator. And that's one shell, and then you can make multiple shells at different heights and different orbital inclinations to serve different customers. Constellations are not new. We've had constellations since the Cold War, but they typically, back then, were you had a couple of satellites, or 4 or maybe 8. In the case of this Soviet Strela 1M constellation, where they had launched 8 at once, and they would operate and then be replaced by another 8. But in those days, the satellites didn't have propulsion, and so they stayed in orbit. And so even though this constellation is all dead, all 360 satellites from it are still in orbit. The more modern constellations before Starlink were, again, they sort of had up to 100 or so working satellites. They tended to be left either have propulsion or be in lower orbits so that they wouldn't litter after they died. The biggest one from a company called Planet in San Francisco has 200 satellites imaging the whole Earth every day. And they have about another 80 that are dead but haven't re-entered yet. So you can see there's a whole bunch already up there in the sort of order, n of order 10 to the 2 regime. But starting with Starlink, we're now going into the regime of 10 to the 3 and 10 to the 4. It's a whole different story. And so as of an hour ago, when 49 more Starlinks went into orbit, so I had 2 versions of the talk, one which had yesterday's numbers and one if this one actually went off, which it did. So we're now up to 3,822 Starlink satellites have been launched, and 544 from the rival British-based company OneWeb. And there are these huge things with 10-meter-long solar panels. These are not tiny CubeSats. They are quarter-ton satellites. But this is just the beginning. And if you look at the license applications to the US Federal Communications Commission, the FCC, and the International Telecommunications Union, the ITU, here are some of the constellations that seem to be more or less real. There's other filings that I haven't included because I'm not convinced that they're really going to happen. Many big constellations, including this ridiculous one from a company called eSpace, telecom mogul Greg Weiler, who's really based in the US, but he put in an application in a kind of flag of convenience way through Rwanda. So Rwanda has informed the ITU that they want 300,000 satellites in this constellation. It is hard to imagine that this is serious, or how they would achieve this, but it is a real application to the ITU, so I think we have to pay attention to it. And these satellites, the Starlinks are currently mag about 5 to 7. The OneWebs are smaller and in higher orbits. They're magnitude 8 to 9. And so those are too faint to see with the naked eye, but still 9 is still pretty bright by astronomer standards. So what do we know about these constellations? When you apply to the FCC, for example, you give these tables. These are 4 different constellations, and they're defined by each constellation has some number of shells, and each shell has a given altitude and inclination and so on. So if we zoom in on the Starlink Generation 2 shell number 3, it's defined as being at 350 kilometers at 38 degrees inclination to the equator with 48 orbital planes and 110 satellites in each of those 48 orbital planes for a total of 5,280 satellites in that shell, which remember is one of like 9. And the whole Starlink Gen 2 is going to be 30,000. So that's actually enough information, given that they're circular orbits, to do a pretty good steady state simulation of what this constellation is going to be like, which I'll do in a while. I just want to show you one of these. This is some OneWebs. This is 36 OneWeb satellites stacked on a dispenser on top of a Russian rocket stage. So this is what the launches look like. They come off the stage, they deploy their solar panels, and here are, from last October, the 426 OneWeb satellites in orbit, and you can kind of make out the orbital planes. And you also see off the coast of South Africa this stripe, which is a bunch of 36 that had just come off the rocket and are still close together and haven't raised to their operational orbits. And so that's one of these trains, like I showed you in the earlier photos. But the story from last year was one of many new entrants in the game. A whole bunch of companies from China, from the US, from Russia, have started launching test satellites for their enormous constellations. 2 or 3, but it's the harbinger of things to come, including this enormous satellite from the Texas company ST Space Mobile, which has a huge communications array that in certain orientations is about Mag 2. So I want to step back for a minute and talk about the overall satellite population to put these mega constellations in some context and show you how things are changing. So I already showed you the plot on the left, which is the number of active satellites versus time, trending up really fast in the past few years. But if you add to that the total number of tracked objects in space, including all the junk and debris, there's about 25,000 objects that the Space Force are tracking, down to about 10 centimeters in size. And the active satellites are, the colors I'm using for them are pink and red, and then cyan to pull out the starlings. And so you'll see that although there's a bunch of them, they're not dominant. And so you might think, okay, this is not transformational. And indeed, when you think about the fact that below 10 centimeters, pencil beam surveys suggest that there could be 1 million objects down to 1 centimeter, which are objects still big enough to really hurt you if they hit you at 17,000 miles an hour. This is, well, what's another few thousand, right? But I'm going to argue to you that that's the wrong way to think about it. Because if you filter this data on mass and on orbital height and look at the ones that are big and therefore bright and low and therefore bright, and skipping over to save time, lots of really interesting stuff you can ask me about later. Here are the ones that are big and bright, more than 100 kilograms, below 600 kilometers. And what I'm showing here is the evolution of the population from 2005 to now, where the cyan is just the Starlink constellation. And so you can see that just in the past couple of years, it has become completely dominant in this category. It's completely dominating big objects in low orbit. And that only 10% of the full constellation is up yet. So, Elon said when he started launching, he said, oh yeah, there's thousands up there already. It won't make that much difference. But this shows no. It's really changing the environment. And it's changing the frequency of close misses and all of these things. It really is a qualitative change. So I'll summarize the slides I didn't show. The upper part of low Earth orbit, above 600 kilometers, is mostly debris. That population hasn't been changing that quickly. The lower part is now dominated by payloads. In 2005, it was dominated by debris. Now it's Starlinks at the big end and CubeSats at the small end. And there's been transformational change in the past 5 years. A couple other things that come out of my database: commercial satellites, which used to be like 1/3 of activity in space, are now vastly dominant over government satellites. And just in the past couple of years, the Chinese commercial space sector, and this is something that doesn't get talked about enough, the Chinese commercial space sector has started to exist and become important. And that's going to have implications when you have many different players from different companies in China who are new on the scene. A lot of our governance methods in space sort of really haven't been incorporating the Chinese very effectively, and we're going to need to. We're not going to have a choice. Okay, so now I want to move on to the actual simulation work that I've done. And so with those constellation definitions that I showed earlier. You can instantiate the steady state of these constellations, assuming they're all in their final orbits. And this just shows you, gives you a sense of the latitude distribution. This is for Starlink, OneWeb, and the proposed Amazon constellation. And they all look pretty much the same, which is that they have very dense coverage between about 52 north and 52 south, and very little coverage in comparison over the poles where there aren't as many customers. So if you live in London, you will have many Starlinks overhead. If you live in Edinburgh, you won't. Unfortunately, the weather at ROE is not great for observing, as I recall from my internship there. Yeah, well, that's also true. So you could look at this and turn it around and ask the question, if I'm at a particular latitude and I'm looking in the sky, how many of these satellites will be overhead, will be above the horizon? And it'll depend on the orbital inclinations of each of the satellite shells. And for each of these colored shells that I have here from a particular planned constellation, they have, this one's a polar one, this one's an intermediate latitude, and then the purple one is a low latitude one. They have these double peaks near the latitude of the inclination of the orbit, little inside. So when you add them all up, what you tend to get is the same as we saw in the previous plot, basically, which is not so bad above 50 degrees, and pretty flat from 50 north to 50 south with details. And this particular one had 4,000 satellites above the horizon pretty much all the time. The good news, of course, is that a lot of these satellites are in the Earth's shadow and are not reflecting sunlight at you. So what you have to calculate is how many are illuminated. And this is pretty straightforward geometry. You basically need to calculate 3 angles. You need to ask, is the satellite above the horizon right now? You need to ask, is it night? Is the sun above the horizon where the observer is? Because if not, it's daytime and the optical astronomers are asleep. And then finally, is the satellite high enough that even though it's night where the observer is, it's daytime where the satellite is and it's illuminated. And so if you have the JPL ephemeris, you know where the sun is, and you can then use your orbit models to simulate this for all the many satellites. And I took a subset of the constellations that I think are likely to happen, excluding this ridiculous 300,000 one. And so that ended up mostly Western ones, one Chinese one at 13,000 satellites, total of 67,000 satellites that we may expect to be launched in the next 5 to 10 years. And so other people are actually trying to work on simulations that would include how bright are these satellites going to be. And I haven't done that for 2 reasons. One was that most of these constellations are basically going to be annoyingly bright anyway, and they're going to be magnitude 5 to 10, and even down to mag 10. That's still a concern. And the other reason I haven't done it is it's a really hard problem to predict. So I've just said how many, let's assume that they're going to be bad, how many of them are there going to be? And I want to emphasize, so if you're in a higher orbit, then each satellite can see more customers, so each observer can see more satellites. But also the satellite, it can see the sun longer into the night, because it's nice and high up. And more subtly, if it's higher, the angular velocity is slower, and so the surface brightness on your CCD of the trail is higher at other things being equal. And so high orbits are bad for the effect on astronomy. Low orbits are bad because the satellites are really bright, and so they might be naked eye, which is bad for the general public, but also Tony Tyson at Rubin has shown that if they're brighter than mag 7, they can actually cause electronic ghosts in his CCD that don't just leave a streak, but affect the whole field. And so that has led to a recommendation to the companies that they should really try and be fainter than mag 7, whatever else they do. Because otherwise, Rubin is going to be in trouble. So here's a reference simulation that I'm going to be coming back to. And what this shows is the number of illuminated satellites as a function of time of night. And this simulation is for kind of the worst case. It's the summer solstice, when the sun is not far below the horizon. It's for 30 degrees south to model the observatories in Chile. And it's only showing how many satellites are actually not above the horizon, but above 30 degrees elevation, because we're professional astronomers and we like to look at the deep sky at air mass less than 2. And so what you see is that in the and so as you go into the night, these vertical lines show angle below the horizon for the sun from sunset at 0 to end of astronomical twilight at minus 18 degrees. And so what you see is that during astronomical twilight, the number of illuminated satellites is pretty constant at about 500 in this simulation. This black line is the total number. I'll go into these details. And then it drops by midnight to only 100. Although the drop is not that fast, and so you have a few hours where it's intermediate. So you might ask, is 100 satellites above elevation 30 bad or good? And I'll argue in the next slide that it's bad, but let's just understand this plot a bit more. So these different colors are the different constellations I'm modeling, and then the black line is the sum of them, right? And so, for example, this red line is the OneWeb constellation in a high orbit. And because it's in a high orbit, it completely dominates. The high means 1,200 kilometers in this case. At midnight, it's dominant. Starlink is these magenta lines, generation 1, generation 2, where they're as bad as OneWeb in the twilight hours, but they drop to pretty much 0 at midnight because they're too low to be illuminated that late into the night. And so the altitude of the constellations is the key thing in what effect they'll have in the middle of the night. Now, just for illustration's sake, I have these two horizontal lines here and here showing the number of magnitude 4 stars above 30 degrees and the number of magnitude 5 stars above 30 degrees. And so you see that in the twilight hours, there will be more illuminated satellites than Mag 5 stars. But remember that a bunch of these satellites are actually going to be fainter than Mag 5. So we're not in the regime in this simulation where the sky is dominated by satellites rather than stars. So what does 100 satellites in the sky, in the upper part of the sky, mean? It corresponds to about 0.04 satellites per square degree. And they're going at an angular velocity, most of them of about 0.35 degrees a second, so it's quite fast. So it doesn't take long to cross your field of view in the telescope. And so you can say, how many streaks do I expect on a typical wide field exposure? If I expose for t minutes in a field of view that is d degrees wide, then I get of order 1 times t times d streaks in my data. So 100 is bad because expecting 1 streak in every 1 minute, 1 degree image, if you're doing wide field studies, is not great. And it doesn't take much tweaking of the parameters to make this much greater than 1. So if you're doing short exposures in a narrow field of view, you're fine. If you're doing long exposures in a wide field of view, you're going to have some issues. So what if you're not observing at air mass less than 2? What if you want to do things all the way to the horizon? Then things are much, much worse. The geometry says that most of the visible illuminated satellites are much closer to the horizon. And so instead of 500 in twilight, you're seeing 4,000 and over 1,000 even at midnight. And that is now much more in twilight than the number of Mag 6 stars above the horizon. So it's going to look like you're near Logan Airport when you're looking toward the horizon once these constellations are deployed. So to recap, big constellations at low altitudes, meaning 500 kilometers or lower, have the potential to be naked eye. Maybe design can mitigate that. You can have many satellites visible in the twilight hours, which is what ordinary people call night, right? Astronomical twilight is what I'm talking about. The first few hours of the night. So it's going to affect the experience of the night sky for people around the world, because they mostly look at the sky, in the early hours of the evening before full astronomical twilight. The big constellations at higher altitudes are probably going to be too faint to be naked eye, but even at midnight in midsummer, they're going to be illuminated in very large numbers, and so wide field ground-based imaging is going to see a lot of streaks. And other people have done very similar simulations. These ones are an update. The ones I've shown you are an update of a paper I published in 2020. Olivier Hainaut, Pat Seister, Kees Basse, and Samantha Lawler have done similar studies that basically give pretty much the same answer. I'll just mention that if eSpace is serious and really launched 300,000 satellites, then it just gets horribly worse with 20,000 illuminated satellites in twilight above the horizon, and really, just then we really will be in the case of many more satellites visible than stars. So I want to go back to this first simulation and ask, okay, but I did give you the worst case, right? I gave you midsummer. And so how do these predictions vary with the time of year and with the latitude of the observer? And so on the right, I have a simulation that's 1 month after the summer solstice, and it is quite a bit better at midnight. Instead of 100 stars illuminated, 100 satellites illuminated, rather, you get only 60 satellites illuminated at midnight. But the slope of this dip, right, isn't so steep. So you're still going to have a significant fraction of the night when there are plenty of illuminated satellites making streaks in your data. If you go all the way to the winter solstice, things are much better. The sun is too far below the horizon to illuminate the satellites. You lose, an hour of your admittedly shorter night at each end of the night. And versus latitude, I show here on the top left at the equator, it's sort of like the winter. It's not a big problem at the equator. I already showed you the 30 north at top right. If you go further north to 46, well, sorry, I showed you 30 south, but 30 north is the same, right? 46 north, it's worse because, of course, the sun is not so far below the horizon, so you don't get the dip in the middle of the night. So if you're living at temperate latitudes like Boston, you'll see a lot of these satellites all through the night in midsummer. But then if you go up to the Arctic, where you'd think things would be even worse, because the maximum inclination of most of the satellites is capped at 50-something degrees, you run out of satellites. And so it's actually better. It's going to be better at the South Pole if you have an observatory there. There won't be so many satellites visible. Good luck with the weather, though. What if you go into orbit? Well, OneWeb is at 1,200 kilometers. That's above most of our LEO telescopes. An HST is currently, it used to be at 600, but now it's only at 540 thanks to atmospheric decay. And that's 10 kilometers below the main Starlink constellation. So the Starlinks are whizzing just above it, as is this Chinese rocket stage, which passed 35 kilometers in front of HST a couple years ago, right through the center of the field of view, blocking this cluster of galaxies it was looking at. So that's what observing a satellite 35 kilometers from you with HST looks like. So Sandra Crook and colleagues have looked at the archive and showed that even before Starlink, there was a serious impact of satellite trails on HST observations at the several percent level, 8% of composite images already affected. And then they model that it's going to get a lot worse, but it's still not going to be as severe as for the ground-based observatories because, HST does long exposures, right? But it has a very narrow field of view. and so it won't catch as many satellites. And also its pixels are very small, and so that cuts the surface brightness. But if you want to launch a wide field telescope to low Earth orbit, as the Chinese are planning to do at the end of this year, I think you're going to run into some real problems. So that's the simulations, but I made some assumptions in those simulations that turn out not to be entirely true. And so I want to talk to you about how we look at what they're based on what the companies said they would do. But what are they actually doing? So we can keep track of them a couple ways. From Space Force tracking data with radars, which is public, and which is passive, so it doesn't require the satellite to be alive. And you get about one orbital data set a day. The downside is you don't get them for the first 2 weeks of the satellite's mission, because when they launch 60 satellites, it takes a while for the Space Force to disambiguate them. So some of the companies, notably SpaceX, provide higher accuracy orbital data from their onboard GPS on the satellites and make that public, and T.S. Kelso at the Celestrak website provides standard orbital fits to these, and so you can use those. And they're available the day after launch, so I should have ones for today's batch tomorrow, I hope. And that's great, but they're only available if the satellite is still working, of course. In fact, that's one of the ways you twig that the satellite has stopped working, if that data stops flowing. And so this allows us to study the orbital height versus time, the orbital plane versus time, all kinds of deployment strategies that the companies never talk about. So you can see a lot from this open source analysis. And I'm summarizing a lot of what we find in this sketch here of the normal life cycle of a constellation satellite, because I think and bear with me because this has implications. So this is based on Starlink, but the others are similar. You deploy it around 250 kilometers. So the x-axis is time in varying units. You raise the orbit toward the operational orbit, but you pause for a month or two at 350 kilometers before getting up to 550. And then you operate, and you operate. Ideally, the nominal lifetime of these things is 5 years, but at least 10% of them operate for much shorter times and then are retired because they develop problems of some kind. So you lower the orbit. Again, you pause for reasons that aren't entirely clear, sometimes for many months. And then you lower the orbit again until you get down to, again, about 300 or 250 kilometers. And then you switch the satellite off. Why do you do that? Because you have these little feeble krypton-powered ion engines. And they can't struggle against the denser lower atmosphere. And so you can't keep the satellite pointed well enough to fire your engine. So you just switch it off and let atmospheric drag bring the satellite in for the last couple of weeks, and it re-enters at some random position over the Earth. And you can sort of see when this happens, because the height versus time is very linear when it's under control, and then it gets curved when it gets into the uncontrolled decay. So here's real data. Here are 60 satellites launched in February 2020. And so you see that they go up, they stay at this operational orbit, some of them are still there, a bunch of them come down, retired early, and note in particular, here this satellite is being lowered in mid-2021, but actually stays a full year in this intermediate orbit. So I guess they were debugging it, hoped to save it, or wanted to study it some more, and then finally let it re-enter in late 2022. And so the point here is that this is not uncommon. Some of them come straight down, but even, this one waited a while, this one waited a while. And so that adds to the amount of time that these things are in orbit, but not in their nominal heights. Now this orbit raising thing, you see the 3 stripes here of orbit raising, is also kind of fun. And so if we zoom in on this, here are the first few months. Launch in February, the 60 satellites split into 3 groups of 20. 20 go straight up to 550 kilometers. 20 wait for a month and then raise. And the final 20 wait for several months and then raise. So why are they doing this? This means that the orbit raising takes over 4 months before all the satellites are operational. And so this is because of differential plane precession. For those of you who are not orbital mechanics fans, what I'm showing here in the blue are these Starlink orbits at 53 degrees projected onto the equatorial plane. So they look like ellipses when projected. And so here's the line of nodes. And because of the oblateness of the Earth, the first order precession effect means that the orbital plane rotates around the equator at a rate of about 4.5 degrees per day. It's really quite significant. Whereas if you're only at 350 kilometers, the red orbits, your orbital plane actually rotates faster. Rotates 5 degrees a day, so half a degree a day faster. So for every month that you dilly-dally in the intermediate orbit, you are changing your orbit plane relative to the operational system, which is rigidly rotating at 5 degrees a day, by half a degree a day. So for every month, you're changing it by 15 degrees. And so this way, by splitting into these 3 groups, with one launch, you fill 3 different orbital planes of your shell for no extra expense. So very clever use of differential orbital precession, I think. But the consequence is that these satellites spend a significant fraction of their lifetimes not at the orbit height I was using in the simulations. So I maintain this page giving all the statistics. The bottom line is that as of this afternoon, 3822 satellites launched, 3530 of them are still in orbit. 300 of them have actually re-entered already. A few percent fail in the higher orbits and are re-entering. I meant to call out, in this plot, the red lines are the failures in high orbit, where the curvature is due to atmospheric drag. So they look very different versus time than the actively controlled ones. And so there's a few that are just going to re-enter in 4 or 5 years. And so currently only 3,100 are at the 550 kilometer licensed orbit in the application. At any one time, so about 3% failed early. So they come off the rocket, something's not right. Either they die immediately, or the mission control goes, this is not going to, this is a potential problem, and so we're just going to let it re-enter and we're not going to raise its orbit. And so atmospheric drag will bring it down in a very short time because they deploy into these low orbits. And so a total of like 4 or 5%, fewer now than in the early days. They really have improved the reliability, are failures, but then also a bunch are just spending a lot of time in orbit raising or in retirement. And so at any one time, 10 to 15% of the system is at these lower orbits, which are then brighter, so bad for us, and passing other systems' altitudes, which is bad for traffic. So you also want to monitor how bright they are. I haven't been doing that work, but a bunch of people have, notably Jeremy Treglow and Reed in Chile, Aaron Bowley in Canada, and so there's extensive work, and they all basically again get the same answer, which is that the Starlinks are about magnitude 5 to 6. The OneWebs are magnitude 7 to 8. The various mitigations that SpaceX has done to make their Starlinks less bright gained like a magnitude, and then they changed the design again, and it lost about half a magnitude, and so it's kind of been a wash at the 1 magnitude level. But SpaceX are actually doing, I'm here to tell you, a significant amount of work to help us. So let me first review the problem. This is what a Starlink satellite looks like. It mostly is in what they call the shark fin configuration. It's like a flat panel TV, about 3 meters long, with a 10-meter solar sail sticking up out of it. That solar sail can rotate to be in plane with the flat panel to reduce drag for when it's doing maneuvers. But when it's operational, it's vertical like that. And so as it orbits toward the terminator with the solar array radially outward from the Earth, the sunlight will scatter off the solar array down to observers near the terminator and will scatter off the bottom of the spacecraft bus to observers a little further from the terminator. So what are you going to do for that? There's a whole bunch of mitigations they've tried. They've changed the attitude control during orbit raising. They tried painting the antennas, but that made them too hot. They tried visors shielding the antennas from reflections. That caused extra drag and got in the way of their fancy new laser crosslinks. So they've abandoned all those. What they have done is change the backing of the solar cell material to a darker color, and that has made the solar arrays less reflective at the cost of making the solar arrays less efficient. And they've accepted that hit. But now they're about to deploy the Generation 2 satellites. They are enormous. They are 5 times the mass, 1.5 tons instead of 300 kilograms. 5 times bigger bus cross-section, a 6-meter bus, 20-meter solar array. Just huge. But they've added on various aspects of it this fancy new dielectric Bragg mirror film that they've developed. Don't understand the physics personally, but the claim is it reduces the brightness, as I'll show you, more like dark paint in various places, and more attitude control strategies, as I'll explain. And the claim is that despite these enormously bigger satellites, they will actually be fainter than the first generation. We shall see. Monitoring is important. So this is, satellite engineers love the BRDF, the bidirectional reflectance distribution function, which is basically like, if you're an asteroid observer, the phase function. The bidirectional is angle of the sunlight hitting the satellite, angle of the observer looking at the satellite. So this is a one-dimensional cut through this two-dimensional function. And the purple line is how bright the satellites are now. And the blue line on this log scale is how bright the Generation 2 satellites are claimed to be. And it's 2 orders of magnitude fainter at many angles. So that would be really nice. Although I will point out that at some angle, the range over the full range of angles is 7 orders of magnitude. And so they can be quite shiny still at the wrong angle. But if this pans out, most of the time these satellites should be quite faint. We'll see. Another thing they're going to do, if you're orbiting, you're trying to get sunlight, you have your solar array looking at the sun. So one thing you can, but that reflects light back down toward the Earth. So one thing you can do is lean back, and that will reflect your light out into space at the cost of reducing your energy generation by cos theta. And they say that they're going to do that in this lower diagram and accept the fact they're going to have a bigger solar array for the same output. They think that that will be net a win for us. And so they really are, SpaceX are putting in a lot of time, money, real time, real effort into making things less bad for astronomy. And that's nice, but there are plenty of other companies, as I've shown you, in many countries. We can't rely that all of them will try and help us. And so we have to work on the broader policy effort. So we're organizing to protect the night sky. We had a working group in the AAS Light Pollution Committee. We had NOIR and AAS organized the SATCON 1 and SATCON 2 conferences. We organized with the IAU and the UN the Dark and Quiet Skies conferences. We presented a report to the UN. We had splinter sessions in Seattle just this month. And last year we had a lot of fun briefing all the various Washington agencies, the White House, the State Department, the FCC, the DoD, and others, to show them the results of our SATCON2 analysis. And so the folks in Washington and at the UN are aware of astronomers' concerns now. And they have taken them on board to a certain extent. Of course, they're also aware that these companies want to make money. And so who's going to win is not clear. So the IAU established its Center for the Protection of Dark and Quiet Skies last year, cps.iau.org. It's still getting organized, but that will be eventually the online center for all the relevant info. We're going to continue working with the various satellite companies on mitigation. I had a good chat with a SpaceX guy at the AAS. We're going to continue, however, public pressure and building coalitions outside of astronomy, because a lot of people care about the night sky. And we're going to carry on working with the UN on the idea that maybe the night sky is part of humanity's heritage and the environment. So I'm going to end this policy section before I wrap up by just leaving you with some questions to think about. Is the night sky part of the environment? And if so, does that mean it's subject to environmental regulations? The Outer Space Treaty says that countries should give due regard to the space activities of other nations. Is astronomy a space activity? It hasn't historically been thought of as one by the space community, but maybe it is, in which case maybe the due regard clause applies. Can we maybe get the UN to say that the night sky is a good thing, we should protect it? Can we get the US, which already issues licenses to companies only if they do a debris assessment to say how much space debris they're going to make, can we get them to do a brightness assessment as well? And maybe even regulate along the lines of you can't have more than X satellites brighter than Y. Right? So those are some of the potential policy directions. And by the way, I am your local representative on the AAS Committee on Light Pollution, Radio Interference, and Space Debris, which is desperately looking for a better acronym, a name. But for now, that's what it's called. So feel free to reach out to me. And I'll leave you with this conclusion. The mega constellations are going to be a significant change to the low Earth orbit environment and to the night sky. But the impact on astronomy depends sensitively on the constellation architecture, particularly the altitude of the satellites. And so again, the low orbit satellites potentially will be naked eye objects, but maybe you can use these clever strategies to make them less bright. They're illuminated near the horizon and not at midnight, so they might be a threat to some astronomy if you're looking at wide field toward the horizon, but most astronomy is not going to be so badly affected by them. It's the higher constellation ones that, although they're not a threat to the naked eye sky watcher, are a threat to professional astronomy because they're illuminated all night long in the summer. And yeah, it's fine in the winter, but for the theorists in the audience, remember, some objects are summer objects that you can only see in the summer, and so I think the LMC might be one, and so it does matter. So I have a web page with lots of references and resources here, and feel free to reach out to me if you have further questions. Thank you very much.
Jonathan. In case you're wondering why planet 4589, that is Jonathan's asteroid. It's 4589 McDowell?
Yeah.
Right. Anyway, questions?
Yeah.
Yeah, Igor.
Well, first of all, to confirm from my experience your HST statement, in 20 orbits that we got in the last couple of months, we got one image affected by a satellite.
Okay.
Which was surprising to us, but anyway.
Surprising that it was so few?
Yeah.
Yeah.
My question is that you completely missed in your talk the geostationary satellites.
I did.
They're actually affecting a lot because the deep surveys are concentrated around the equator.
Mm-hmm.
And for instance, from Arizona, you cannot observe really I think it's UDS, so there's a field at -4 degrees where all those things project. And once we had a mask, spectroscopic mask, with the vertically located slits, and all of them were just crashed by the stuff, because you have magnitude 10, magnitude 11, and it just crosses the 1 arcsecond wide slit, and it's enough to kill your Redshift 7 galaxy.
Now, that's very interesting. Yeah, yeah. I mean, I will say the thing about the geostationary satellites is that situation hasn't been changing rapidly, right? That's been the case for a long time, and we're seeing all of the change we're seeing in the satellite population has been in the low orbit stuff. But you're absolutely right. It's important to worry about them too.
Other questions, Charles?
So, will the locations of these objects be known with any precision, so that one could actually potentially schedule around them?
Right. That's the challenge. So for the ones in operational orbit, using the SpaceX ephemeris, it's probably accurate enough to get it within at least an arc minute, right? So how accurately do you need, right? You don't probably need to know where it is in your field, but you need to know that it is going to be in your field. So I think we can, as long as we get predictions of maneuvers and things like that, right? And so we have been working, that's one of the main discussions we've been having with the companies, is please give us this kind of ephemeris data. If we just depend on the two-line elements from the Space Force, they're probably not good enough to do a really good job of that avoidance stuff.
Oh, yes.
Yes, up there. Hi, Yvette.
Very nice talk. So you and I both seem to have an appetite for people yelling at us on the internet. I think it's fair to say.
That is fair.
A lot of very opinionated people talk about this issue and and one of the common things I often get is people are like, why don't you just filter out like the time when the satellite is tracking like in time or something like that? So what's your response when people surely ask you?
Right, yeah, and so that's, the one I get more often is, why don't you just move all ground-based astronomy into space? Because that'll be easy.
I think everybody here already knows why.
But yeah, we won't have to explain to this audience why that's not really feasible right now. But why don't you just have a shutter that cuts out the data for that 1 second that the satellite goes over? That'd be great. If you can do it in software. I don't think, Igor can correct me, that most imagers have that capability right now.
You can close for optical imager easily the shutter, but you have to time it. There is capability, but there's no manpower to implement it. That's
the thing. Yeah, I mean, you could do that. It's an unfunded mandate, right? So it's not going to be cheap to do that on all telescopes. It's not going to be, and it's not clear that these orbital data are accurate enough with the timing, right? If you're a second off, it doesn't work, right? And so I think we will be forced to that, but it's not trivial to implement.
Oh, lots of other questions.
Yeah.
What, if any, requirements are there to bring these down when they're done working or?
Right. So the license requires you to explain your get rid of it strategy, and historically it's been like, even if you go bust, the company that inherits your debts, inherits the responsibility to get these things out of space. And so SpaceX have said that their Starlinks are designed to be what they call fully demisable. They burn up completely on re-entry. And they're in these low orbits, and so they'll come down within a solar cycle or so. OneWeb at this higher altitude will be up for centuries if they fail. So they have to be much more reliable. But they have, the idea is still that they will have enough propellant to lower their orbits unless they fail.
Yes.
Hi, John. This is maybe more wishful thinking, but the Iridium project in the 90s failed because of lack of interest, really, finances. So just looking at the numbers, satellites being launched, they surely not every one of them is going to have business enough to keep them operational. Do we have any indication yet as to whether the SpaceX satellites, for instance, or one of the other constellations, is actually getting the response that they're expecting?
Right. Are they actually going to make a profit?
Yeah.
Well, I mean, profitability is so last century. I think Iridium went bankrupt. They got bought. They're still in business. They launched a new generation constellation. So they're still going, despite having, not made money for a while. And so, I think it's too early to tell. I think it was slower than projections, the uptake of Starlink. And they've had problems rolling out the service, the practical parts of the service, like getting antennas to the users, right? I think the success in Ukraine of getting communications to people in Ukraine has sort of changed the dynamic of that a bit, and they're probably going to have a certain anchor customer near DC that will ensure that they'll make a profit. That's my guess. But not all of these companies will survive. That's for sure. Some of these systems will go bust, and will they successfully retire? You know, Iridium said when they were first launched, "Oh yeah, even if we go bust, we'll deorbit all our satellites." And they had like 80, and 30 of them just straight out failed and couldn't be deorbited, and they're still up. None of them are still up there. So SpaceX are doing better. How these other companies will do in terms of reliability remains to be seen.
Well, one more
Okay.
question.
How does this relate in height to where the space station is, or where our other scientific satellites are? I mean, do we
Great
have,
question, yeah.
Do we have to drive out of the way in case it's
Well,
happening everywhere?
SpaceX says, "Trust us, we'll dodge you." So on the way up, they go through the orbits of the Chinese and international space
Yeah.
stations. And the China complained because a couple of the Starlinks actually moved, one on the way up, one on the way down, moved more close than they were comfortable to their station. And SpaceX said, "Well, we were fine. You know, we didn't go that close to you." And the problem is this: that the U.S. then went, "Oh, you see, SpaceX are right, China's wrong. There was no threat. Our models show that it was an easy miss." But these are not regular satellites that just orbit ballistically, right? They're running their electric propulsion systems all the time. And so that means your ability to predict where they're going to be tomorrow is substantially poorer than if you know that they're not actually firing their engines.
Yeah.
When you take that into account, I think China were right to complain. Because again, if I'm an astronaut on the Chinese space station and SpaceX tell me, "Yeah, we'll miss you by 100 meters, it's no problem," that I'm maybe not entirely comfortable with that.
Okay. One last question.
Okay.
Yes?
Thank you very much. Great talk. Very naive question. If two different companies want to launch satellites on the same orbit, how is it decided who can do what?
That's a great question. So if they're from the same country, that's the responsibility of the licensing, the FCC, for example. If they're from different countries, there's nothing to stop that right now. Geostationary satellites have slots that are allocated by the International Telecommunications Union, more for stopping radio interference than for stopping collisions. But low orbit satellites are not regulated in that way. And so there's absolutely nothing to stop China going, "Yeah, we're going to use the same orbit as SpaceX and we'll just dodge best we can." And the problem is, the companies all go, "Oh yeah, our automated avoidance systems are really good and there's not a problem." I'm just not confident about the systematic tails of their error distribution, So I feel we may learn some hard lessons that way.
Okay, I think we have to wrap it up here. If you would like to join us for dinner, just come and talk to me after the talk. So let's thank Jonathan again.